All right, in our last video, we looked at function notation. There's another notation we need to look at for describing sequences, lists of numbers, and that is called recursive notation. So, to begin with, why do we need more notations? What's the whole point of this? Well, recursive notation is very handy when you're looking at that list of numbers and you can explain exactly how to get from the number that you're at right now to the next number in the list. This is a good notation for doing that. And it's especially useful when the input values, the starting places, really only make sense as whole numbers. So when we're talking about whole things like animals or people or variety of things like that, that don't make sense as continuous functions. Okay. So, and just generally the points of having notations in the first place, these are our shortcuts for lazy mathematicians, so that we don't have to write so many words, but we have to get everybody to agree on what's happening, and the way that we get people to agree on them is when they're in high school, we teach them these things, so that later on everybody can talk together and understand. So here's going to be my first example. We're going to do this kind of by example. I've got 4 pictures here. Each picture is something that happened to the previous picture along the way. So hopefully you can see what's happening here if I analyze that this green square right here is maybe this green square, and then it got these 2 added onto it and this one up here. And so in this next one, I can see here's my original green square and the 1 blue and 2 blues this way that got added to it, and then we stuck 1 on the top again, and then 2 to the right, and I think I can see that that is the pattern that's happening here. So if I had to add another one to this picture, I would have a pretty good idea of how I was going to do that. This one, I can see where I put 1 on the top here and 2 more out this direction. So every time I'm sticking 1 new one on top and 2 more off to the right. That's how this pattern goes. Okay. And if my concern here at this point is maybe how many blocks or how many squares do I need to make these pictures, I can count up my totals along the way, and it took 1 square to make the first one, and 4 to make the second one, and 7 to make the third one, and 10 to make the fourth one. And if I look for a pattern in that list of numbers, I think I could describe that pretty easily. So every new picture needs 3 more squares. Okay. And then I'll put them where they are supposed to go so that I get the shape that I'm looking for. So in words, the description here is that every new picture needs 3 more squares. Okay. So what is that in terms of the notation? Okay. So the first piece of notation we're going to introduce is A of 1. A of 1 stands for the number of squares that we need to make the first picture. This 1 in here is not the 1 square. The 1 in here is the picture number 1. Okay. A sub, or A of n, okay, A of n is what we're going to use to represent the number of squares in the current picture. Whatever picture we have right now, whatever picture we happen to be looking at, we're going to refer to that as A of n. We could, of course, if the n was 3, it would be talking specifically about the third picture, but more generally here, A of n will be the number of squares in the picture that we are currently looking at, and a of n plus 1 will be the number of squares in the next picture. So if n is where we are right now, 1 more than n is moving to the next picture down the line. Okay, so picture a of n and picture a of n plus 1 are always right next to each other. Okay, one right after the other. So how do we use that notation? Okay. Well, first of all, in words and trying to connect with the color codes that I have on here, the number of squares in the next picture, so here is in red, the number of squares in the next picture is 3 more than, okay, I don't have the 3 more than captured in any of my notation here. It's 3 more than the number of squares in the current picture. Number of squares in the current picture, that was my green one, that was this one. Okay. So symbolically, what does that look like if I actually make use of those symbols? Well, it says the number of squares in the current picture is 3 more than the number of squares in the current picture. So 3 more than means that I'm going to add 3. So this, as it's written here, in words would say the number of squares in the next picture is the number of squares in the current picture plus 3. It's equivalent to what we have in the words right there. Okay. Okay. All right, but this is missing something. It's not enough for me to just tell you how many more you need for the next one, because I never told you where to start in the first place. If I say I'm thinking of a list of numbers, and the way you get from one place in the list to the next place in the list is to add 3, and I ask you what's the next number, well, if I never gave you a starting point, then you have nothing to add 3 onto. So we need to know this extra piece of information, that there is 1 square needed for the first picture. Remember our notation up here for number of squares in the first picture. We need to say that the number of squares in the first picture was equal to 1. So, putting this all together then in symbolic form, and I'm just going to write it all out right now and see if I can remember all of my colors, we would say that the number of squares in the next picture is equal to 3 more than the number of squares in the current picture. There's my current picture plus 3 more. And then I put a semicolon at the end of that, and I say, and the number of squares in the first picture is 1. Okay? So that gives me my starting point. I can look at that and I say, okay, the first picture has 1 square, and then this tells me that if I want to know how many are in the next one, then take how many I have right now, which is 1, and add 3. 1 plus 3 will give me 4 that are in my next picture. Okay. Now, there are variations on this. Not everybody does this with parentheses. Sometimes they do it with what are called subscripts. Okay. And when we read it, we say the sub part. We don't say all of the subscript. So I read this one as A sub 1. And this one I can read as A sub n. Okay. Writing it over again doesn't help anything. A sub n, and this is A sub n plus 1, they still stand for the same things. This is still the next thing here. This is still the current. And this is still the first along the way. So writing the equation above in this notation would look like a sub n plus 1 is a sub n plus 3 semicolon and a sub 1 is 1. Okay. So sometimes you will see that. I think we will be sticking with the function notation that was up here. In this class, of course, we assume that you have seen this before. You may not remember it real well, but it shouldn't be completely unfamiliar, and we're going to need that in some of the stuff that we got coming up here soon.